Hello all. So today in this session, we'll see how do we solve an unbalanced transportation problem with maximization as the objective. We'll do this based on a particular question, a problem we'll take, and we'll try to understand that. How do we solve it? Question is like this. A company has plants at A, B, and C which have capacities to produce 300, 200, and 500 kg respectively of a chemical per day. The production cost is known to be 70, 60, 66 respectively for each of these plants. 4 bulk consumers have placed orders as given in the following table. So consumer 1, 2, 3, 4 and how much they require. So this basically is your demand quantity, whatever is given in the second column. This price offered subsequently will be your selling price. So that is your price offered. And the capacities, this is nothing but the supply quantities. Then further, they had given us shipping costs in rupees per kg from plants to consumers. Plants means ABC, consumers means this 1, 2, 3 and 4 are given again. So means if I consider this particular 9, it is the transportation cost or shipping cost from plant B to consumer 3. It is 9 rupees per kg, right? For this situation, we are supposed to find what will be the optimal schedule. So what is the first step? First step is to check whether the given problem is balanced or unbalanced. So sum of the supply is nothing but the sum of the production capacities what are given in the question. It is given as 300, 200 and 500. If we add those, we get 1000. Then sum of the demand, so that is quantity required per day in kg, that is also given for each consumer. So it is 400, 250, 350 and 150. So that works out to 1150. So here we may note that the sum of supply is not equal to sum of demand. So we call this as an unbalanced problem. So before we start applying any algorithm, we need to first make it a balanced one. How do we do it? Here we may note the sum of supply is lesser than sum of demand. That means we are supposed to bring in a dummy supply point or dummy row. So that corresponding cell entries will have zeros in it, and the supply quantity for that dummy point will be the differential quantity. What do we mean by differential quantity? This 1150 minus 1000 will be your differential quantity. So 150 will come in the supply, it will come as a supply quantity for that dummy point. So further we may note that the question is given as the price offered to each customer, and then it is also giving you production cost per kg, and a table is given for shipping cost from each source point to each destination point. So when we have this price offered to customer, production per kg, and then shipping cost per kg, we can able to calculate profit per kg for each combination. What combination? Plant versus consumer combination we can able to form. How profit will be price offered per kg minus production cost per kg minus shipping cost per kg. So since the matrix will have the cell values as unit profits, the entire matrix will have unit profit per kg, how much is the profit. That means our objective will become now maximization, not minimization, because we are supposed to maximize the total profit. So we create a profit matrix like this. So for consumer 1, the price offered, if we know it is 100, this is whatever I'm marking here, that is your price offered. So for consumer 1, it is 100 rupees. For consumer 2, it is again 100 rupees price offered. For consumer 3, it is offered as 102. And for consumer 4, it is 103. So that is the base. I mean, that is the price which is going to be offered. and the 70 rupees is for this particular plant. That means plant A, if I produce that particular product, then the cost of manufacturing will be 70. So let me mark that cost is 70. So likewise for B, it is plant B, it is 60 rupees production cost. Plant C, it is 66 rupees production cost that is getting subtracted. And the other numbers, that is this 3, 5, 4, 6, this is already being given in the shipping cost. From this table, it is being taken 3, 5, 4, 6, 8, 11, 9. So the corresponding cells are getting minused with these numbers if you look into. The 3 getting minused in the first cell, then 5 is getting minused in the first row, second column cell, and then first row, third column cell, you are subtracting 4. So by that, we can create what is called as a profit matrix. Here, it is also written after balancing. So that means we already introduced a dummy, which will have 0 as the cell entries, and this 150 is our differential cost, right? That is what it is. So we created this profit matrix, and let us move on further. So this is our balanced profit matrix. The previous slide and this slide is same. Only difference is that all these explanations is not given straight away. This 27 is written, 25 is written. So that is what is this particular slide. Then any algorithm, if you want to use for finding the basic feasible solution or for finding the optimal solution, we need to ensure that the problem is of minimization type. But whereas the earlier matrix, whatever we had is a profit matrix, which means the problem becomes a maximization type, which means we are supposed to convert that into a minimization type. How do we do that? We identify from all these cells, what I mean is this, from all this entire matrix, what is the maximum cell entry? So if I compare all these numbers, that is 27, 25, 28, 27, etc. up to 0, 0, 0, the maximum we may identify it as 34. That means if I have to convert this profit matrix to a loss matrix, what I should do is I should subtract all these elements, that is this 27, 25, 28, 27 from 34 to get the loss matrix. That is what we would have done it in the subsequent this thing. For example, 7. How we got this 7? It is nothing but 34 minus 27. Then the next number, 34 minus 25. We got this 9. Likewise, all these cell entries are evaluated. Means all the cell entries we got now for this loss matrix is subtracting from 34 with these entries. So 34 minus 27, 34 minus 25, 34 minus 28, and so on. 34 minus 0, 34 minus 0. So that is what gives you the loss matrix. Once we arrive at a loss matrix, now we know clearly that now the objective becomes minimizing of losses. So we can now proceed with finding the basic feasible solution. How do we find? So we will use Vogel's approximation method, wherein we will find what is the penalty for each row. So let us calculate the penalty for each row. First row, the least cost in the first row is 6. Next least is 7. So the penalty becomes 1. Second row, least is 1. Next least is 2. Penalty is 1. Third row, least is 0. Next least is 4. The penalty is 4. Last row, least, next least, both are 34 only. So the penalty becomes 0. Coming to columns, let us calculate penalties. First column, least is 2. Next least is 4. Penalty is 2. Second column, least is 5. Next least is 6. Penalty is 1. Third column, least is 0. Next least is 1. Penalty becomes 1. Fourth column, least is 3. Next least is 5. Penalty becomes 2. So what is the next step? After identifying the penalties, you need to identify what is the largest penalty among all these penalties. So 2, 1, 1, 2, 0, 4, 1, 1. So naturally the largest is 4. That means we are supposed to do our first allocation to the third row. Means this row. Which cell? The cell which has got the least cost, which is here. 0 is the least cost. So come to that particular cell, compare the supply quantity, corresponding supply quantity, and the corresponding demand quantity. We may note It is 350 and 500. So the least is 350. So allocate 350 here. Since I allocated 350 here, no more allocation here, no more allocation here, no more allocation here. Close this. This column is over. Close this penalty. Since 350 is already done, 500 will reduce to now 150. Now, after every allocation, you have to recalculate the penalties. Now, first row, least is 7. Next list is also 7. Because this column is over, you can't consider 6 now. Least is 7. Next list is also 7. So, penalty becomes now 0. Second row, least is 2 now. Next list is 3. No change in the penalty. It remains 1 only. Third row, least is 4. Next list is 5. Penalty changes to 1. Last row, no change because 34 and 34, it remains 0 only. First column, 2 and 4, no change in the penalty. Second, 5 and 6, no change in the penalty. Third is already over. Fourth, least is 3, next list is 5, penalty remains as 2. Now comparing with all these penalties, 2, 1, 2, 0, 1, 1, the largest is 2, but it is occurring in 2 places, in the first column also, in the fourth column also. Theoretically speaking, you can use any of them arbitrarily, you can choose any one, but we will just go logically. If I choose the first 2, then we'll be in a position to allocate to this cell, which is the least cost cell. If we go to that cell, we may compare the supply quantity is 200, demand quantity is 400, which means we will be able to allocate 200 here. Suppose if I choose this 2, then the least cost cell is this cell, wherein the supply quantity is 200, demand quantity is 150. That means we'll be allocating 150. So it is better to choose this 2 because we can able to allocate more. So this 2, if I choose, I will compare 200 and 400. We will allocate 200 here. Since this 200 is fully done in the row, I'll close the cells, other cells, and then cut this, cut the penalty. Since 200 is already done, this 400 will now reduce to 200. Right. Now recalculate penalties now after every allocation. So first one, 7 is the least, next list is 7, no change. Second column, second row is already over. Third row, least is 4, next list is 5, no change in the penalty. 34, 34, no change in the penalty. Coming to column, now first column, least is 4, next list is 7, penalty changes to 3. Second column, least is 6, next list is 9, penalty changes to 3. Third column is over. Last column, 5 is the least, next list is 7, no change in the penalty. Now if we compare all the penalties, the largest penalty is 3. Again, it is occurring in 2 places, first column as well as second column. If I choose the first column 3, I'll be allocating here, then it will be 150 and 200 comparison of 150 and 200. So we'll be allocating here 150. Suppose if I choose this, we'll be allocating here. There also it is 150 and 200, you will be allocating 1. So any one you can choose, I will choose the first one. This first 3 means I'll allocate here 150. Since I allocated 150, I'll close this, close this, close this, close this. 150 is already done, so this 200 will reduce to now 50. Recalculate penalties. Again, go back to first row. Least is 7, next list is 7, no change. Second row, third row is over. Last row, 34, 34, no change in the penalty. Coming to the first column, 7 is the least, next list is 34. So this 3 will reduce to now, sorry, it will change to now 27. What is the 27? 34 minus 7. Then second column, 9 is the least, next list is 34. Penalty changes to now 25. 34 minus 9. Then coming to the fourth column, 7 and 34, the penalty changes to 27. Now what is the largest penalty? Now it is 27, which is occurring in 2 places. It is occurring in first column also. It is occurring in fourth column also. If I choose the first column 27, then we will be allocating here. That means we will be comparing 50 and 300. You will be able to allocate 50 here. Suppose if I choose this 27, then we will be allocating here. So then we will compare 150 and 300. That means I'll be allocating 150. So it is better to choose this 27 because we will be able to allocate a larger quantity. Means I'll allocate here 150 by choosing the fourth column's 27. Since I allocated this 150, I'll close this, close this, close this. Since 150 is already done, this 300 will now reduce to 150. Recalculate penalties. First row, least is 7, next least is 9. Penalty changes to now 2. Second row is over, third row is over, last row 34, 34, no change. Coming to first column, 7 and 34, no change in the penalty, it remains 27. Second column, 9 and 34, no change in the penalty, it remains 25. Third column is over, fourth column is over. Now among this, that is 27, 25, 2, 0, largest is of course 27. So we'll be allocating to this particular cell, that is the cell having 7, right? So 150 and 50 you will compare and you will allocate here 50. Since I allocated 50, I need to close this, close this, close this. Since 50 is already done, this 150 will reduce to now 100. Now, recalculate penalties. Coming to first row, only one cell is left, that is 9. 9 minus nothing, that means 9 minus 0, the penalty changes to 9. Now, second row is over, third row is over, last row, 34 minus nothing, because no other cell is there to allocate. 34 minus nothing means 34 minus 0, so this changes to 34. Coming to columns, in the second column, 9 and 34, no change in the penalty, it remains as 25. Third column over, fourth column over. That means we have now 3 penalties. One is 25, another one is 34, third one is 9. Among this, the largest is 34. So here you have to allocate, only one cell is there to allocate, 150 or 250. So you will naturally allocate 150 here. So close this, close this. Since 150 is done, this 250 will reduce to now 100. Now, only one cell is left. When I calculate penalties, 9 minus 0, it remains 9. And column wise also 9 minus 0, this penalty will change to 9. Now, when you come to the last cell, penalty should match, quantity also should match. Whether the quantity is matching, we can verify 100 and 100. Of course, it is matching. So allocate 100 here. Now, let us check whether this is a basic feasible solution or not. There are 4 conditions for basic feasible solution. First 3 conditions, any of the algorithm will automatically satisfy those 3 conditions. Only the last condition we are supposed to check. What is that last condition? M plus n minus 1. What is m? It is number of rows. How many rows? There are 4 rows. What is the number of columns? N is number of columns. It is also 4 minus 1. That means we are supposed to have 7 allocations. Do we have 7 allocations or not? 1, 2, 3, 4, 5, 6, 7. Yes, we have 7 allocations. So we can conclude the above is a BFS. So since we got a BFS, we can proceed whether to check whether this is optimal or not in the next slide. So whatever allocations we did now, we have to put it there in the next table. So same thing only I would have put 50, 100, 150, 50, 100, 150. Then in the 200 next row, then 150 and 350, 150 and 350, yes. Then 150 in the last row. Yes, we have done all. So for optimality, we need to use UV method, wherein we will be considering U1 as 0. We'll do this finding of UIs and VJs for the allocated cells. How we do that? UI plus VJ should give you the corresponding cost. Means this U1, suppose if I come to this first allocated cell, what is the cost here? 7 is the cost. Means the corresponding U value is 0. Corresponding V value we don't know. But if I add this U and V, I should get this 7. That means 0 plus something, I should get 7. So that something should be 7 only. Coming to the next allocation, that is here. 0 plus something, I should get this 9. So that something should be 9. Move on to the next allocation. Here it is. 0 plus something, I should get 7. That something should be 7. Now, go back to the first column again. In the second row, something plus 7, I should get this 2. Something plus 7, I should get this 2. So that something should be minus 5. Then come down further. 7 plus something, I should get 4. So that means this something should be minus 3. Then in this row itself, there is one more allocation here. Minus 3 plus something, I should get 0. So that means this something should be 3. We can come down. 9 plus something, I should get this 34 because there is an allocation here. 9 plus something, I should get 34. That means this something should be 25. Now we got all UIs and VJs. Now we can find out what is the delta IJ. So how do you find delta IJ? It is done for all unallocated cells. Delta within brackets will be Cij minus of Ui plus Vj. That is what you have to do. So wherever the brackets are written, those are the unallocated cells. Directly we can do the calculation. Means whatever is within brackets we have to do first. Means I have to add the Ui and Vj first. That is 0 plus 3. It is 3. Then it has to be subtracted from the cost. That is 6. So 6 minus 3 becomes 3 only. Then here 9 minus 5. 9 minus 5 is 4. Then I have to subtract that 4 from this 5 to get 1. Coming here 3 minus 5. 3 minus 5 is negative 2. Then we have to subtract this negative 2 from this 1. So 1 minus of minus 2. It becomes 1 plus 2. So it is 3. Coming here 7 minus 5. It is 2. Now we have to subtract that 2 from this 3. So 3 minus 2 is 1. Coming here 9 minus 3. It is 6. 6 has to be subtracted from this 6. So it becomes 0. Coming here 7 minus 3. It is 4. So 5 minus 4 gives you 1. Coming here 7 plus 25. It is 32. This 32 has to be subtracted from this 34 to get 2. Coming here 3 plus 25. It is 28. 28 has to be subtracted from 34, which gives you 6. Then the last one 7 plus 25. It is 32. 34 minus 32 gives you 2. Now we may note all the delta Ij's here, 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 here. All the brackets are all greater than or equal to 0. We may note all delta Ij's are greater than or equal to 0 because there is 1 0 there. So what is the conclusion? Since all the delta Ij's are greater than or equal to 0, we can conclude that we had reached the optimality. However, this third row, second column position delta, that is delta 3, 2. What does it mean? Delta sitting in third row, second column is 0. We can see that. Third row, second column is 0. So that means this problem has alternative optimal solution. Means without change in the total profit, there can be different allocations profit. So possible, right? Here you may note it is not total cost, it is total profit. Means only for doing or applying the algorithms, we are converting profit to loss because you need a minimization problem. But subsequently, when you actually calculate, since the original problem is of profit, you need to calculate profit only. So let us see how do we calculate or how do we present our optimal solution. So first allocation, X11. If we look into first allocation is sitting in first row, first column, then first row, second column, then first row, fourth column. All those will be mentioned here. First row, first column, first row, second column, first row, fourth column. Then whatever quantities we had, we are mentioning that. Then in that table, we can get the loss. Now that loss has to be converted again to profit because the original problem is of profit only. How do we convert? All these numbers, that is 74, sorry, 7, 9, 7, 2, all this has to be again subtracted from 34 to get these profits. Or the original matrix, whatever was the profit in that particular cell, we are considering those. Then to calculate the profit, this is profit per unit. We are going to allocate 50 units, which means 50 into 27, we get this. 100 into 25, we get this. Then the final total profit is 30,700. So this is the optimal solution for this. Suppose if you want to find out what is the alternative optimal solution, you apply that theta method, which we learned in the previous class. How do we allocate theta? So what do? You allocate to the least negative delta ij value. Instead of least negative, here you will be allocating to that particular cell which has got the 0 in it. And then you identify what is the theta value, maximum theta value possible, and then create a new table and proceed and find out what will be the new allocations. That is the way you do your alternative optimal solution. Means in that again, the profit, the total profit will remain the same. Only the allocations may change in few places, or in some of the places it may change. So what we learned today is about how to convert an unbalanced problem to a balanced problem. And suppose the cell entries we land up with, or if the cell entry is given or something related to maximization, how do we convert that maximization to a minimization problem? Then again, we use the same method, that is Vogel's approximation method, to find out the basic feasible solution. And after finding the basic feasible solution, we proceeded with UV method to find out what is the optimal solution. So that is what we had seen today. Thank you very much. We'll meet in the next class.